Before we pause for a short coffee break, let us welcome our last speaker for the first session of the day, Melvin Xin Jie, who obtained his bachelor degree of engineering in chemical engineering from Sweden University of Technology, Sarawak. With his presentation titled The Potential of Co-pyrolysis of Empty Fruit Punch and Disposable Face Mask Bases, let us welcome Melvin onto the stage for his presentation.
Good morning, ladies and gentlemen. My name is Melvin from Curtin University, Malaysia, and thank you, I.K.A. POPSIG, for inviting me to talk on my research project, which is the potentials of co-pyrolysis on fruit punch and disposable face mask waste. So here is my presentation outline for today, and without further ado, let me start off with the background of the study. Malaysia is one of the top producers and exporter of palm oil in the world. However, it is crucial to understand that in the process of harvesting 1 ton of fresh fruit fibers, it creates 0.5 to 0.7 tons of the palm oil meal effluents, as well as 0.37 tons of solid waste such as empty fruit bunches. And as the demand increases, in view of these other users in the other industry, this will in turn create an abundant waste that needs to be rid of. Current biomass utilization, elimination methods such as direct combustion, as fertilizers and landfills are not environmental friendly option to do so. And on the other hand, the global pandemic has switched up the norms of our daily lives. We wear face masks every day as a social distancing guidelines method to reduce the spread of the virus. And yes, I know some of the mask mandates in other countries has also lightened. And Malaysia, for example, has lightened their face mask mandate recently. However, the accumulation over the past 2 years globally has made the surge of plastic waste into it to also cause some soar in the reduction efforts. And also, these surgical face masks are considered as a single-use plastic waste, which contains 73% of the polypropylene plastics and 13% of the polyethylene plastics. The consequences of this single-use plastic waste is actually it causes microplastic pollution in the water bodies as well as landfilling. One way to utilize this, the abundance of this waste, is to convert them into renewable fuels through the biochemical methods as well as the thermochemical methods. For my research project, I utilized the thermochemical method, such as the pyrolysis method, because it is fast, simple, and uses a high conversion rate. My research also combines uses the technique of co-pyrolysis of biomass, the empty fruit bunches, and plastic waste, the face mask waste, and with the addition of a catalyst to which in most papers has stated that it has a strong selectivity of desired aromatics. It's a simple configuration design which can be used as an alternative for some pretreatment processes such as hydrogenation, and it reduces coat formation on the catalyst, which will help to prolong the lifetime of the catalyst use. So in layman terms, my problem statement for my research project is can we reduce this waste through co-pyrolysis, and is it worth it? My research that has been identified is the thermokinetic data of the co-pyrolysis process of the empty fruit bunches and the face mask waste, and the synthesized bio-oil product quantity and quality. My aim of the project is actually to identify the thermokinetic parameters of the co-pyrolysis process and to determine the bio-oil yield and compositions of the bio-oil. To achieve this, I have several objectives, which is to perform thermogravimetric analysis, PGA, and substitute into the distributed activation energy model as a kinetic modeling tool. Secondly, to synthesize bio-oil through the furnace tube reactor, and to analyze the bio-oil via the gas chromatography mass spectrometer, GCMS. for my methodology, I split into two parts, which is the first part is the thermogravimetric analyzer. I can collect the TGA data from this process and substitute into the distributed activation energy kinetic model. With this, I can actually identify the thermo-kinetic parameters such as the free exponential factor, the activation energy, the change in enthalpy, the change in entropy, and the fixed free energy. The second part of my methodology is the furnace tube reactor or the pyrolyzer, where I can synthesize my bio oil. And with the synthesized bio oil, I will analyze the bio oil through the GCMS to identify the compositions of the bio oil, as well as the carbon number and the product distribution. So here are my results for the TGA. For the co-pyrolysis of EFB and P at the end, I identified two peaks from the process. The first peak identified is actually just the degradation of the biomass constituents, such as the cellulose and hemicellulose. And the second peak identified is the decomposition of lignin, as well as the decomposition of the plastic constituents, such as polypropylene plastics and polyethylene plastics. Next, I also run several heating rates, such as 10, 20, 50, and 100 degrees Celsius per minute. And I found out that when shifting to higher temperature heating rates, it's actually increased the thermogravimetric curve actually shifts to the right side, which is called a thermal delay phenomenon, where the temperature gradient is being formed from the outer layer of the particle to the inner side of the particle. However, this actually helps to increase the degradation rate, such as here, at 10 degrees Celsius per minute heating rate. The peak one from 5.28% per minute actually increases to 53.6% per minute degradation. Next, I place the thermo-kinetic. I've determined the thermo-kinetic data from the distributed activation energy model. I've modified it into this model with a high accuracy of the coefficient of elimination or R-square value of more than 90%. For the single feedstock of the EFB, I identify the activation energy to be 79% or close to 80%, and the exponential factor of 1.52 to the power of 10 to the power of 5. With the co-pyrolysis process, this activation energy actually reduces, which is in line with the assumptions we the hypothesis, which is the co-pyrolysis process actually helps to reduce the activation energy. And with the addition of the nickel catalyst and the ZSM5 catalyst, this activation energy actually further reduces to 54.22, which is the lowest activation energy that I have collected. With this, I can also further calculate the thermodynamics parameters such as the enthalpy. And I found that with the enthalpy actually reduces accordingly, and it is in positive values, which means the process is endothermic. Next, I have also, for the product yield, I have also identified that the single feedstock of EFB produces 16.11% of bio oil, and it also has the highest selectivity for biochar at the highest of 37.33%. However, with the co-pyrolysis with the face mask, this biochar actually helps to reduce to 31.55%. And for face mask, it has a higher selectivity for biogas production at 99.17%. So by comparing the co-pyrolysis process to further improve the bio oil yield, I also use the nickel catalyst and the ZSM5 catalyst. From this comparison, I found out that by using ZSM5 catalyst, it helps to increase slightly for the biofuel group and reduces the biochar yield by quite significant amount to 26.84%. So I also qualify my biofuel by using the GCMS. I found that for EFB, it has a higher selectivity for aromatics, and for the phase mass, it has a higher selectivity of aromatic hydrocarbons, which is the alkanes and alkenes. And the co-pyrolysis actually consists of both, which is as expected. And interesting enough, the ZSM5 catalyst actually helps to boost up the aromatic oxygenase, which is what we want, because it contains the phenols and all the value-added chemicals. Furthermore, with the co-pyrolysis of EFB and EFM, the carbon number range from the analysis actually helps to reduce to C6 to C8, which reduces the EFM at the phase mass with carbon number range of C3 to C30. With the addition of the zeolite catalyst, on the other hand, this carbon number range also reduces to C3 to C30. With the highest selectivity for C6, the phenols, at 38.28 to 6%. So moving on to my research impact, I compared it with the compliance with the SDG, which is number 7, 12, and 13. For number 7, it is to produce value-added products of bio-oil and with improved bio-oil quality. And number 12 is to have a cost-effective alternative, such as pre-treatment or hydrogenation, and contributing to the circular economy for the palm oil industry, while solving the abundance of the palm oil waste. Number 13 is to create solutions to reduce the greenhouse gases while reducing the face mask waste going into our water bodies, causing microplastic pollution. For my future study, I will continue my research with the parametric study of temperature and fixed ratio, and to model fit it to other models and compare it with the literature. And lastly, the thermo-economic analysis, which is to run some simulations and to do the feasibility studies. So for my conclusions, I've determined the thermo-kinetic parameters such as the activation energy and pre-exponential factor and the change in enthalpy and entropy. I found that with the addition of zeolite catalyst, I can achieve the lowest activation energy of 54.22 kilojoules per mole. And for my second objective achieved, which is to determine the bio-oil yield as well as the quality, to improve the quality of the bio-oil yield using zeolite catalyst, as well as co-pyrolysis process. Next, I will further thank my supervisory team for the support and guidance for this project. And here are my references cited. And I would like to further extend my appreciation to a.k.a. POPSIG, the Smart Biosphere and MONG for the bursary support. That's all from my team.